My name is Kevin Freeman, and my project was predicting antimicrobial resistance using census data. So the data set. What really inspired this was this data set from the CDC. They collect antibiotic resistance data by state. So what it really is how in each state, what percentage of the microbes in the hospitals in that state were antibiotic resistant. So they've got this handy viewer, and then you can download the data as a CSV file. So that data wasn't really sufficient for building a model because really all it tells you is the antibiotic resistance. There aren't really any explanatory variables. So I went to the US Census Bureau and downloaded some data on demographics in each state. I downloaded one table that was the population estimates in each state divided by sex and by age, and I combined that with another table that was the urban and rural households in each state. So I combined those data and then combined them together with the antimicrobial resistance data, and that formed the data set that I did my analysis on. The business problem, obviously, it's antimicrobial resistance, but why is this such a problem? Well, 2 million people in the U.S. become infected with antibiotic-resistant bacteria each year, and this results in 23,000 deaths. Also, even when people don't die, this prolongs their treatment, prolongs their stay in the hospital, and makes their treatment more complicated, and it costs the healthcare system $30 billion annually. That's just in the United States. So it's a very costly problem in both lives and in just monetary terms. And by building these models, I'm hoping to identify what factors lead to antimicrobial resistance. And if I can build a model that has a high predictive accuracy, maybe it could be used as a way to predict future outbreaks of antimicrobial resistance. Data exploration. So I'll go over to my code for this part. The first thing I did to explore the data was I looked at the response variable, which is percent resistance. I decided to focus in on MRSA data only, so that's why it says MRSA data. But the data set includes a lot of different antimicrobial resistance data. So in this MRSA data, I made a histogram of the response, of the percent resistant. I found that across all states, most of the data falls into this like 40 to 55% resistance range. There's maybe a little bit of a right skew with all these states that are in the 30 to 35% range, but overall the data seems relatively normally distributed and there's not a lot of outliers. Then to explore the explanatory variables, so that's like population data by age, urban-rural data. I did some correlation. I found that a lot of the data is highly correlated with each other, which I kind of expected from the nature of the data. For example, percent rural has a negative correlation with total urban. Age under 5 has a negative correlation with median age. Age 85 plus has a little bit of a positive correlation with median age. And so that means that in my models, I have to either account for this correlation or just not use models that assume independence. I also did principal components analysis. I found two PCA in my scree plot. I found two PCAs, or two principal components, were enough to explain most of the variation in the data, and these first two components, none of the variables loaded on just one of the components very directly. We've got these diagonal lines. So, it kind of makes sense because I'm really only looking at urban, rural, and age distribution. So two principal components probably should be enough to capture all that variance. The last thing I did to explore the data was I plotted these first two the scores from these first two components, and I plotted the states along those axes to see if the states clustered in groups that made sense. So I've got this little cluster, Maine, Vermont, West Virginia, New Hampshire, like relatively rural states with a lot of open spaces, California and Texas, really big states over here with some urban clusters. So that shows that these features are picking up on something interesting in the data. At least there's at least some separation in the states. So that was about it for my data exploration. Now to go on to data transformation. So I didn't do too much data transformation. The two things I did was, what I really did was I just created some derived features. So I took this urban-rural data. I took total urban area, urban cluster, and rural. These are all variables that were in absolute number of households that are rural or urban or in an urban cluster. And then I divided it by the total number of households in the state. So I got, percent urban, percent rural instead of absolute population. I thought that would make the data more comparable across states. And I did the same thing for the age values. So, for example, age 65 plus, instead of just absolute number of 65 plus year olds, I did 65 plus divided by total population. Pretty simple transformation. Next, the models. So my three models I used were a linear regression model, a random forest model, and a KNN model. What I was really focusing on here was interpretability, because one of the outcomes that I want is to be able to identify which features are the best predictors of antimicrobial resistance, so then we can get some kind of idea of what causes antimicrobial resistance to spread. So I chose these three models because they're all really interpretable, and and they all work as regression models. And now I'll go into how I trained them and how they performed. So the first model was a regression model. Here we go. I trained the regression model and then used stepwise backwards elimination to eliminate variables until I got the optimal set of variables, using AIC as the elimination criteria. My final model used total urban area, total male population, age 85 plus, age 65 plus, and median age as its predictors. And then down here, I calculated the root mean square error, which I'm going to use to compare between all the models. I just used the model to predict all the state antibiotic resistance, percent resistance data. And I got a root mean square error of 6.66. So this is, we'll see how good this is when we compare it to the rest of the models. So the next model I used was a random forest. Again, I chose a random forest because I wanted the option to be able to, look into that decision tree and see where it was making its decisions, if this turned out to be the one that was getting the best results. I used tenfold cross-validation to test the model, used root mean square error as the criteria, and then I tried 6 different values for number of features to look at each branch. So I trained the model, here's the results. The best number of features to look at was 6, and I got a root mean square error of 8.22. So that is worse than the linear regression model, but remember the linear regression model, we got some feature selection. So let's try using the same features on a new random forest model and see if that improves it, and see if we can do better than that original linear regression model. Same as before, using tenfold cross-validation. This time I'm only looking at 6 features, so I'm only considering 1 through 6 for the number of features to look at each branch. And here we go. How we do? In this example, 4 features was the best number to look at, and I got a root mean square of 8.16. So better than the last random forest, but still not as good as the original linear regression. Next, KNN. So KNN is the only model I used where it needs the features to be in relatively the same range, so I used max-min normalization. You can see the minimum for every feature is now 0 and the maximum is 1. Then I split the data into a training set and testing set. So 80% in the training set, 20% in the testing set. I used this FNN library because class does not allow you to train a KNN model using regression. And yeah, I trained it, and then on the test set I got a root mean square error of 8.24 using k equals 6. So that's not so good. It's about on par with the random forest, but a lot worse. But significantly worse than the original multiple regression model. So let's try different values of k. I tried 3, 6, 12, 15, 24, 30, 35, and 40. I found that 30 was the best value of k, and it got me a root mean square of 6.68. Which is pretty good, but still not as good as the original linear regression model. So again, same as the random forest, I'll try that smaller set of features. Again, 30 performed the best, and it got a little bit better. So the root mean square was now 6.77, so it improved a bit, still not as good as the original linear regression model. Now, the ensemble method. I stacked these models and then used a linear regression model to create my ensemble method. So I had them predict on the test set of data. I fed the predictions into an ensemble model, a linear model right here, and then calculated the root mean square of their predictions. So I got 5.71, which is better than any of the models alone, but this still might not be that useful in a real-world context. I'm going to remind you about the range of the percent resistance. So it ranges from 32.5 to 67.8. That's a relatively small range, like 33%, and we're off by about 5.7% each time. So how useful would that really be in a real-world context? Probably not. So the summary, what I learned, my main takeaway is it really depends on what data you give your models, how good of a result you're going to get. I think the data I gave my models was really insufficient. It only captured a couple aspects of the data, which were age distribution and that urban-rural divide. I think if I added some data about like healthcare specific statistics, maybe wealth data, that would give a better model that might be more useful and more give us insights that we could actually use. Right now I think my model is just not really good enough to draw too many conclusions from. Thanks for watching.